One of the most powerful tools we can use to analyze the motion of objects is actually utilizing energy and the conservation of energy to figure out what happens at various points in an object's motion. This can be used in conjunction with kinematics and things along those lines, but I found that the conservation of energy and analyzing the energy you have before and after an event is one of the easiest ways and one of the most straightforward ways to get as much information as possible. So I'm going to show you a few examples, show you the main underlying concepts, and show you the method that I have found over the years tends to be the easiest to follow and is very straightforward. So if we want to analyze the transfer of energy of an object or a system, we just have to remember the law of conservation of energy. The total energy you have before an event has to equal the total energy you have after. Now the forms can change as we've discussed, but the total you have before has to equal the total energy afterwards. Now we're going to specifically look at mechanical energy. So we only have three types that we've discussed: gravitational potential energy, kinetic energy, and elastic potential. And those three, when I add them up, that gives me my total energy before, and that has to be equal to those same energy types, but you may have a different amount of each. So whatever I have before in total has to equal the total afterwards. Once I kind of see this, I can simply substitute my actual mathematical expressions for these energies. mgh for gravitational potential, 1/2 mv squared for kinetic. And for now, I'm going to leave elastic potential energy as EEL. We'll look at the mathematics behind the energy stored in springs and like elastic bands. But for right now, I'd like to focus mainly on gravitational potential and kinetic. So we'll come back to this quantity in a future lesson. But for right now, I am going to leave it in there in case it's provided in a problem. The only difference between these two is obviously this side is based on all of your initial values, and this is based on all your final values. So your initial height, your initial velocity, your final height, and your final velocity. So the individual energies may change, but the total you have before and the total you have afterwards should be the same. So just let's go right into an example so we can see how all of this applies. So if we have some kind of ball that has a mass of 10 kilograms and a velocity of 12 meters per second, initially, that's before, it's going to go flying up this ramp, and over here, right when it's at the peak of the ramp, we know that it's now 3 feet high, so we want to know how fast is the ball traveling, and we're going to assume for this problem that this surface, both of these, frictionless. So we don't have to worry about any kind of energy losses as we did with our roller coasters. So as you can see, ignore these red crossouts for now. I start with the same equation I had before. My gravitational potential plus my kinetic plus my elastic potential energy before must equal those same three types, the total of those three, afterwards. Now I've crossed out any energy types that I don't have. So I have no height here, so I have no gravitational potential. There's no spring anywhere here, so I have no elastic. But I am moving, so I have some kinetic. And over here, I've gained height, so I certainly have some gravitational potential. I still have some kind of velocity, so I have kinetic, but there's no spring, so there's no elastic potential energy. So if I take a look at what I've removed, I'm only left with the kinetic energy before and the combination of the potential and kinetic afterwards. And the law of conservation of energy says that these two values have to be equal. If I just substitute these variables for the actual equations I use to calculate them, you get 1/2 mv squared before has to equal mgh plus 1/2 mv squared afterwards. Now it's just a matter of plugging in the values I know. The mass is 10, the velocity is 12 in the initial case, and the mass is 10, the height is 3, and the mass is still 10 in the after case. Once I set this up and I equate my before initial values and my final values, you'll see that the only variable that's unknown is velocity. By solving for velocity, I get 720 joules of energy initially. I get 294.3 joules of potential energy afterwards. And I have 1/2 mv squared of kinetic energy. Because these all have to be equal, I can solve and find that that ball must be traveling at 9.23 meters per second. So again, just to quickly recap, I just take the total energy I had before, mechanically, and the total mechanical energy I have afterwards. remove whatever energy sources we don't possess at either of those cases, and then it's just a matter of substituting in the equations we know. Once we've done that, you just need to solve for the unknown variable. I'd like to quickly go over a second example, this one where you do have friction and therefore work is performed on the system. So here I have a block that's 8 kilograms. It's sliding to the right at 5 meters per second. Friction, however, is slowing it down. The box's displacement is right. The force of friction acts left. So because those are opposite, hopefully you're realizing that the work performed is negative due to the difference in direction of the force and the displacement. And therefore, it's going to steal energy from the system. It's going to convert it to heat, sound, non-mechanical forms of energy. Afterwards, it slides to rest, so its final velocity is 0. You'll notice that even though I'm dealing with a different situation, now there's friction, the process is identical. Well, I look before my total energy types, and that has to equal the total mechanical energy afterwards. There's no height before, so I have no gravitational potential. There's no spring, so I have no elastic potential. And afterwards, I have no height, no velocity, and no spring. The problem you run into now is I'm left over with EK here, kinetic energy, and over here I have none. Now that's a problem because this seems to violate the law of conservation of energy. Energy cannot be destroyed, so I can't start with some here and end with nothing. But in order to set these two equal, the fact that I have none just tells me that work must have removed energy from the system. So that just means I started with kinetic energy here, and I have no mechanical energy left. The mechanical energy, the gravitational potential, kinetic, elastic potential, that's gone. It must have been converted to some form of dissipated energy, something like sound, heat, light, etc. So this just means I have no mechanical energy. It means that work has been performed. Anytime you set these two equal to one another and there's very clearly a violation or appears to be a violation of the law of conservation of energy, that simply means that work has been performed. So you'll see all I did over here was added plus work to this equation because I need to account for the work that left the system. Once I've done that, you can see that all the kinetic energy I had before left the system as work, and now I just have to plug in the variables I know. EK is 1/2 mv squared, so that kinetic energy initially must equal the energy that I lost through work. Plug in the values I know, and you'll find that 100 joules of energy left this system. So it was originally kinetic energy here, 100 joules, eventually was dissipated as heat, sound, probably wouldn't have any light in this situation, but some other non-mechanical form. All 100 joules has left the system.